Hello, everybody, and welcome to today's webinar. My name is Ayla Stiegler. I'm with the scientific group here at Wolfram Research, and I will give you a quick introduction of today's presenter, Konrad Szymański. Konrad holds a PhD in physics and is now a postdoctoral researcher at the University of Siegen in Germany, where he's currently working across different subfields of quantum mechanics. While his PhD research was mostly about the geometry of quantum states, he is now concentrating on the application side of things, aimed at trying to find a way to use quantum computers when irreparable noise is present. Today, Konrad will be talking about the topic of his PhD research, which is titled Numerical Ranges and Quantum and Geometry in Quantum Information, Entanglement, Uncertainty Relations, Phase Transitions, and State Interconversion. The relation of numerical ranges to their convex duals, the Spectrahedra, connected with convex optimization tasks, is showcased along with the intuitive meaning of both structures. The usage of Wolfram language for visualization and addressing related physical questions is explored. With that, Konrad, I'm handing over to you. Thank you so much.
Thank you very much for the introduction. Yes, I will try to keep the presentation accessible to everyone. It's not only meant for people working in the field of quantum information. So, if you have any questions, please ask them in the Q&A section of the seminar. And well, let me begin with the very basics. So, what is quantum information even? So, you perhaps remember. Some of you perhaps remember the Schrödinger equation. Right? So it's essentially a wave equation which describes the movement, the evolution of an electron in a central field, like in a hydrogen atom. And the space on which the Schrödinger equation works is essentially infinite dimensional. If we have two solutions, we could add them together. If we have three solutions, we could add them together and the result would still be a solution. But in principle, we could add an infinite number of solutions and the result would still describe a movement of evolution of an electron. But what happens often in quantum information is that we restrict ourselves to only a finite subspace of the entire space of possibilities. So, for instance, if we have an experiment, we could restrict ourselves. We just have a rubidium atom trapped in an optical trap, for instance. We could restrict ourselves only to several energy sublevels because we are certain that the evolution will be constrained only to some of them. And sometimes the constraints are completely natural and dictated by the underlying physics. For instance, the polarization of a photon is described only by two parameters. So the amplitude, you could think about them as an amplitude of the horizontal polarization, or the amplitude of the and the amplitude of the vertical polarization, or the clockwise and anti-clockwise circular polarizations. So the field of quantum, most of the field of quantum information takes place in the finite-dimensional complex Hilbert spaces. Essentially, we take d photons from 1 to d, we add them with certain complex amplitudes, and that's our d-dimensional space we are operating in. So, for instance, in the case of hydrogen atom, we could take these two wave functions describing the electronic states of the hydrogen, and we could span the entire space with only these two, and we would have a qubit, a two-dimensional complex space. So if we have this we have restricted ourselves already to finite dimensional subspaces, we could start thinking about measuring things. So how does it happen? Well, it's a very complicated question. We don't fully understand the details up to this point of time, but we more or less understand how it begins. So we have this electronic degrees of freedom, for instance, in an atom, and we couple them to the outside world. So in the case of a hydrogen atom, it could be just a spontaneous emission. We have an excited state, eventually it's going to emit a photon, and that's essentially coupling to the electromagnetic field. So we coupled it to the outside world, and our aim in an experiment is to create a large-scale spatial separation so that we have a clear interpretation of the result. So, for instance, the atom could be a different. If it's one of these two states, it could emit one wavelength or the other, or one polarization or the other, and we just have a light, a mixture of different polarizations coming to a measurement device. So what we could use is, for instance, if it's a mixture of different polarizations, we could use a polarizing beam splitter, which lets horizontal polarization pass. Horizontal polarization pass, but reflects the vertical polarization. So when the photon eventually arrives in one of these two detectors, we are certain in which polarization it was. So what we are counting in an experiment are just the photon counts of vertical and horizontal polarizations, or it could be different wavelengths of light. So that's the basic scenario. So that we have this internal degrees of freedom. We have coupled them to an outside world for like the electromagnetic field or under all the various scenarios. And then we have measured this. Then we have measured this outside world macroscopic degrees of freedom, in which we have clear interpretation of the result. So indirectly, we are measuring all the coefficients ck in a state vector. And this is a point of contention within physicists. The fact, where does this rule of probability come from? So, I mean, when there are three physicists, there are four opinions, essentially. Some say that it's the only possible mathematical choice, that we have the initial state. We'll always measure the end result with probability of like absolute value squared of ck, and that the probability is always proportional to that. That's known as the Born's rule. And there are various different interpretations of quantum mechanics, but the fact still remains that that's the thing we observed. We can always only observe the coefficient squared, the absolute value of coefficient squared in a certain orthogonal basis of the system we are trying to measure. So we often interpret this basis of orthogonal vectors as the eigenbasis of some Hermitian matrix in this reduced finite-dimensional subspace, so that the physical operator matrix X is just, you can decompose it in the eigendecomposition as a projector, so normalized projector onto one of the states, times the real associated eigenvalue. And then we could start thinking about measuring expectation values. Because expectation values, if you just do a little bit of algebra on the probabilities and on these previous expressions, you will quickly see that the expectation value of X, so the eigenvalue times the probability of which you get the eigenvalue, attains this form. So this is essentially just a bilinear form with X as the matrix in the middle, right? And then, so for instance, we have these two matrices, and we could start just by measuring x1 on the state vector ABC. And it will take the following form. All right, so if we have measured a single expectation value, and remember that it's all coming from experiment, we measure these different counts. visualize these different counts, we can sometimes just switch the device setting and measure x2. Or we can switch them back and forth and measure both of them, essentially, if we are sure that the device is always producing the same state. So, for instance, we could try to measure the expectation values for, well, just a random vector. And we get two expectation values, one for each of the x1 and x2 in this three-dimensional acute read system. And the joint numerical range, so the very topic of my PhD research, is essentially the set of all allowed expectation values. So if we have, we'll just start with a single point. We add one for just a random vector, another one, and if we add enough of them, we start to see some set appearing in the plane. And that set, if we were to check all of the different vectors, that set would exactly be the joint numerical range of x1 and x2, these two operators. And you can always generalize it to 3 operators, 4 operators, etc. Although it gets increasingly complicated, more complicated to visualize these sets, especially for high-dimensional ones. And the matrices are Hermitian. That's what we measure. So the coordinates are real, because you can simply prove with a bit of linear algebra. And this set is explicitly constructed as a convex hull. So the set always is convex. It doesn't have any holes. It doesn't have any bumps in the surface. It's entirely defined by the boundary. And the thing about the connection to the quantum information is that these sets are in principle measurable. So the story behind this picture is while I was still a student at the Jagiellonian University, there was a visiting mathematician, Stefan Weiss, with whom I'd be working to devise a classification of the shapes of three-dimensional numerical ranges. So 3 operators like this, of size 3. So these are exactly 3 by 3 matrices. It would be a classification in terms of ellipses in the boundaries of flat parts and how do they connect to each other. Well, he done most of the part of the actual classification. I was mostly providing examples. But recently I found out that someone actually observed these three-dimensional shapes in an optical experiment. So that's really surprising that someone would implement a purely mathematical result from the field of linear algebra as a real world experiment. So these are measurable in principle because they are just expectation values. And we could visualize them. We could visualize them with a bit of random search. Essentially, that's a Monte Carlo algorithm. But there are other options, more involved ones. So the thing is that, well, we can just observe. You can ask a question, what is the rightmost point of this numerical range? It's still for the same 3 by 3 matrices. The rightmost points are the one that maximizes x1, expectation value of x1. And if you think about it, it will be just the point corresponding to the eigenspace to the maximum eigenvalue of x1, because all of the vectors in the numerical range have to be normalized. All of the vectors which give rise to numerical range have to be normalized. So the norm has to be one. If you maximize over all possible vectors like this, you will essentially just settle down on the maximum eigenvalue or the eigenspace to the maximum eigenvalue. And it holds not only into this particular direction. This will be the image of the eigenspace to the maximum eigenvalue of x1. But you can ask the same question about what will be the point at the at the very top of the numerical range, the one that maximizes x2. And that will be the image of the eigenspace, the maximum eigenvalue of x2. And the same reasoning will work for arbitrary direction, essentially. And that's how we could build the numerical range from outside. So that's how you can phrase it mathematically, that if you maximize a certain linear form of the numerical range, you will get the maximum eigenvalue of a compound operator like this. These are the two operators which define the set. And then, well, let's just start with a previous algorithm for that and add some interior points. Then we could start exactly building the boundary of the numerical range from outside using this observation. And you see that's a much more efficient algorithm. The first one is perhaps more is much simpler, but well, this one offers a much higher speed. So that would be one thing we could start. We could tell about the numerical range, but if we want to actually use it in quantum information, we have to get into the mathematics side of things, unfortunately. So yeah, I already told that the numerical range is convex. It's explicitly constructed as a convex set, a convex body even. So it's a finite. It's closed and well, it's a compact set, the convex compact set essentially. Let's assume that it also contains the origin, which is not that great of a deal, not that great of assumption, because we can always shift it if it doesn't. So we can always just rescale certain coordinates, and well, that's essentially it. And if we have a convex set like this, then we can say that it's defined by family of linear inequalities, because you see, the joint numerical range we had before is defined by the linear inequalities. All the points have to be in this half space. That's a half space defined by a linear inequality. All the points have to be in this half space, and so on and so forth. If we make an intersection of all of these half spaces, we would get the numerical range, because it's a convex set, and such sets are defined by intersection of half spaces like this. So we get something like this, that if we only if we only knew the support function h of n, which is the normal vector, the vector along which we normalize the maximum eigenvalue, essentially, in this case, the x is contained in the convex set if and only if for each direction it fulfills the linear inequality. So we could use the linear inequalities as our new parametrization. Essentially just rescale n, like get this h of n into here, so that the inequality is bounded from above by unity. And then we have the dual set. The dual of a convex set which contains the origins, a convex compact set, looks more or less like this. We had points on the boundary previously with a certain normal. So the red arrow here is the point on the boundary of the set, and the green arrow here, and the green arrow corresponds to a normal point. And the normal points get mapped to the points on the boundary. The normal vectors get mapped to the points on the boundary of the dual set, while the coordinates here get mapped to the normals in the dual set. So essentially, we can still reconstruct. If we know only the dual set, we can still reconstruct the original one. So this point has an entire family of linear inequalities, because you see it has different normals. All the green vectors correspond to different normals, but they are supported by the same point. And it's a complete duality in the sense that the same, like the dual of the dual is the set itself. If we start from this set and try to work out its dual, we'll get the same set, the original set, and also the normals in this set get mapped to points on this set and vice versa. So what does it give us in the terms of numerical ranges is that we exactly know the linear inequalities numerical range has to fulfill. Simply from this observation we had before, which we used to visualize the numerical range, that the maximal of such just a linear function, all of the points of numerical range is just a maximum eigenvalue. So therefore, the dual of a numerical range of two operators x1 and x2 will be the set of all normals for which this linear function maximized is lower than or equal to 1. And we can substitute this maximum with just maximum eigenvalue of x dot n. So this will be just sum of ni times xi for all of the different operators. Therefore, we are just looking for normals for which this maximum eigenvalue of this matrix x dot n is lower than 1. And with just a little bit of linear algebra, and you can convince yourself that it's exactly the condition that unit matrix, the unit matrix, 3 by 3 unit matrix in this case of operators we're talking before, unit matrix minus x dot n must be positive semi-definite. So it's a matrix, so this is a matrix for which all of the expectation values are larger than 0, essentially. And this is a thing called a spectrahedron in the field of convex algebraic analysis. And the thing about spectrahedra is that they have explicit polynomial descriptions, because the boundary is exactly the set of points for which this positive semi-definiteness criterion barely fails. So perhaps you remember from your algebra class the Sylvester criterion for checking whether a matrix is positive semi-definite is essentially that you take all the different leading principal minors of a matrix. So you take submatrices of the original matrix, calculate the determinant of them, and if all of the determinants are positive, then the matrix is positive semi-definite. Is positive definite, but for positive semi-definite matrices, so one of the eigenvalues could be 0, but it can be negative. We have to take all the leading minors and define the spectrahedron exactly. So the set of parameters n for which this matrix is positive semi-definite. And let us now plot the spectrahedron corresponding to, well, essentially the same matrices. So as before, so matrix from so the matrix as we had before, and this is exactly the spectrahedron attached at the unit matrix and spanned by these two. So you can observe that the eigenvalues of matrices corresponding to the point inside the spectrahedron are always all positive, right? But as we get closer and closer to the boundary, the minimum eigenvalue gets smaller and smaller, and eventually, as we cross the boundary, one of the eigenvalues is negative, at least one in this case. So minus 0.5. And this is exactly the dual set to the numerical range of these two operators. As we can observe now, you remember this is the numerical range of these two operators. We have a flat face on the bottom, and what you remember perhaps about this this convex duality is that flat face gets mapped to a cusp. And if we had a flat face here in the dual of the numerical range, which is the spectrahedron, we would get a cusp here, but it's not present in this case. So this flat face has only a single normal vector for all the points here, but there are like an entire family. There is an entire segment of the coordinates which belong to the flat face, and it corresponds to the normals of this. To the normal vectors in the spectrahedron. And this is a kind of big deal because spectrahedra have explicit polynomial descriptions with these determinants. If we just parameterize this matrix 1 minus x dot n with n and calculate of the determinants, the result will be just a set of polynomials. If all of them are positive, then the matrix is positive definite. And that's what I call the polynomial description. Therefore, we could start using these numerical ranges, because if the dual has a polynomial description, we can hope for the polynomial description of the numerical range itself. And all of the measurable quantities, all of the things that you can observe in an experiment, are expectation values. The probabilities of certain outcomes are expectation values. All of the statistical moments of the operators that you observe are also expectation values. The variance can be constructed from these expectation values, I will see shortly. And therefore, the numerical range is often the right tool to analyze certain problems in quantum information. So perhaps you remember the Heisenberg uncertainty relation. So the variance of an operator will be just the expectation value of an operator squared minus expectation value of the operator. Well, the expectation value gets squared, just like in normal everyday probability theory. So you remember the Heisenberg uncertainty criterion, that the variance, if you observe a particle, if you observe the position of a particle, you build statistics of all of the different positions. You run the experiment several times, you get a nice distribution. You can calculate the variance of this distribution, and then you calculate the variance of a momentum distribution. You observe the momentum of the particle, the velocity essentially. And what you observe is that if you multiply these two variances, there is a lower limit to the product of variances, essentially. The product is bounded from below. However, in this finite dimensional quantum information, the sum of variances is more natural because, well, the variance of a certain operator will be zero on its eigenvectors. And if you just multiply this zero by a finite variance of the other operator, you'll just get zero. So the bound will be trivial for whatever operators you choose. So that's why you use the sum of variances. And it has a really nice form, because if you just plug this expression here, you can observe that this x squared, the x1 squared can be joined with x2 squared. And we have a function which depends only on 3 expectation values. So the sum of 3 variances. The sum of 2 variances is a function of only 3 expectation values, and we can use the 3-dimensional numerical range. So x1, which will be one of these operators, x2, and a compound operator made from these two. This 3-dimensional numerical range will be entirely sufficient to determine the minimal sum of variances, and you could do it numerically. This will be the 3-dimensional numerical range. And by the way, it will be a nice point that if we have a 3-dimensional numerical ranges like this, so in Mathematica, that's essentially what's called a convex Hall mesh. You can always just export. You can always just export them. You can always just export them, this 3-dimensional object, to an STL file which is recognized by, which you can then directly print on a 3D printer if you have one. So we have this three-dimensional numerical range. And what we want now is to minimize the sum of variances. So we have x3, so the third coordinate minus first coordinate squared minus second coordinate squared. And you see that the set of constant sum of variances must be a paraboloid of revolution. Therefore, our aim is to find now a paraboloid of revolution of a certain form, which barely touches the joint numerical range from below. So it's barely tangent to this three-dimensional object. And that would be about here, I guess. Yes, I think so. So I mean, this family of paraboloids might be tangent for multiple values of this shift C, which is the sum of variances, but the paraboloid evolution for which the shift is minimal corresponds to the minimal sum of variances, essentially. And we could use this polynomial description of the joint numerical range to obtain the strict solution to this problem, not only a numerical one, because well, the dual of the joint numerical range is a spectrahedron. All the constraints of a dual set are also polynomial, also just polynomial constraints, essentially quadratic constraints. So we can just build, that's essentially what this function is doing. We can build a set of polynomial equations and try to reduce some of the variables using Gribner basis. So for two operators, it works perfectly. For three operators, you have to be careful because the analog of what's known as Kippenham's theorem does not work completely, but you can always fix it manually, just remove some of the parts that come out. I mean, there is a systematic method to do it, but it goes beyond the scope of this talk. But we essentially have a polynomial like this. So this is like a polynomial in three variables, and this is the set of solutions to this polynomial. And if we just plot the joint numerical range of these three operators now, you will observe that the joint numerical range here, calculated numerically, is the convex hull of the sets of solutions of this polynomial. And since we have the polynomial description of this numerical range, and the paraboloid of revolution is described by a polynomial equation, we could, in principle, just solve them together to find the minimal sum of variances. And that's exactly more or less what's happening here. So that's what the polynomial describing the sum of variances looks like. It's zero essentially for the sum of variances for which the paraboloid of revolution is tangent to the numerical range, and the minimal root of the polynomial will correspond to the minimal sum of variances. It might have complex roots, of course, but we are looking for a real root, and you will observe that the numerically found minimum sum of variances, which essentially is just evaluated over the different points of the boundary of the numerical range, calculated using the Monte Carlo technique described before, is equal to the minimum sum of variances calculated using this approach of polynomial equations and Gribner basis. So that could be one thing about the connection between numerical ranges and the problems of quantum information, and it actually has found some uses in the field of spin squeezing, for which these x1 and x2 operators are spin operators of certain of certain spin representation, so J1, J2, and so on, and you can find then the minimum sum of variances essentially corresponds to spin squeezing inequality, so that you would get a minimal variance of the maximum Fisher information of maximum Fisher information for measuring certain rotations using these spin systems. But that's not all of them, because you can use also the joint numerical ranges for entanglement detection. So just a very basic primer. If we have two systems, essentially, and the two states in the two systems, so here alpha and beta prepared by two different devices, or controlled by a computer perhaps, but that's a classical link. Then the joint state might be of this form, that it's essentially just a tensor product or Kronecker product of alpha and beta, or it's like a statistical mixture of states like this, so that we could have some correlations between the two different subsystems. But for like each experimental run, you could be certain that you are given just one part of the state, and it's entirely definite. It's not entangled with the others. And entangled states are exactly the states for which such decomposition doesn't exist. It's not a product, or it's not a statistical mixture, statistical ensemble of such states. So a state, a classical state, could have form like this using the Kronecker product. So if we have like a two-dimensional qubit on one side, and described by alpha 1 and alpha 2, two-dimensional qubit on the other side is described by beta 1 and beta 2. That would be the Kronecker product and the tensor product of the state in the compound four-dimensional space. And how we can use these numerical ranges? Well, we could make a very similar algorithm with what we had done before. Just sample random states, but in this case, they would be random product states. And then, if we just take a convex Hall mesh, you have to believe me on that the convex Hall mesh will take care of the statistical mixtures by itself. And what we will get in the end will be the set of allowed expectation values, but only the classical ones, only the expectation values which are able to be explained using this model that we have a computer or something controlling two different boxes, and you have two different states going on each side. So that would be a separable numerical range, and it will look more or less like this for like a two qubit operators. Yes. So these are the three operators essentially just the computational basis of the qubits. And the blue ball, the blue sphere, is the joint numerical range. So it's the set of expectation values for any states, entangled states or not. And the red object inside, is the separable numerical range for these three operators. And therefore, if you have these three-dimensional sets pre-computed, and you observe these the expectation values, so you have these three-dimensional objects pre-computed, and then you go to a laboratory and you try to measure the expectation values of these three operators in the same recipe we had before. We just couple these two systems to the outside world, we measure, or we obtain the statistics, and we get the expectation values. And you observe that your triple of numbers, the three expectation values you get, well, they have to be inside the blue region, but they possibly could be outside the red region. And then you are certain that your state, the state that your measurement device, that your device is producing, must be entangled, because it's not explainable by any model like this. It's not just two devices working perhaps in tandem but controlled by a classical link. It must be, there must be some non-classical correlation thing going on, essentially. And that's perhaps a very basic algorithm to calculate a separable numerical range. There are much better ones, but it still gives you a taste on what they could be used for. So these could be the two things that I think are most important for a presentation like this. If you just remember that there existed things called numerical ranges, and they are the sets of allowed expectation values for quantum mechanical observables, and that they are dual to spectrahedra, so affine subsets of the set of positive semi-definite matrices, so the matrices for which all the eigenvalues are non-negative. These two sets are dual to each other, and they are both easy to visualize. And if you have three-dimensional objects, you can even 3D print them. That would be about it. There are some uses in quantum information, but there are also multiple open problems, both from the quantum information, side of things, and also in the mathematics side. So a more mathematical question would be the classification of the geometry of these three-dimensional numerical ranges, because you remember this slide. This is essentially the geometry, all allowed geometries of three-dimensional numerical ranges of operators of size 3, so 3 by 3 matrices, and there are 3 of them. So the classification is known, but for 3 4 by 4 matrices, almost nothing is known, and that's the problem I'm working on right now. But also from the physics side of things, you remember that the points at the boundary correspond to the eigenspaces to maximum eigenvalues. But if you invert the inequality, you can just about think of them as minimizing the eigenvectors to minima eigenvalues, so the ground states of certain Hamiltonians. They encode the properties of like zero temperature quantum mechanical systems in a way, and you can use them to analyze an Ising model. Simple, and I have done it in my PhD thesis if you want to see. And you can use them. You can use them to, for instance, find the current state space is gapless. Is gapless, so there is no gap in the total, the total Hamiltonian. But for what else you can use it for? Well, it's an open question. And also some other problems which would require perhaps more introduction, but you can always read the PhD thesis to see what I'm talking about. All right, thank you. We can go to questions, I think. So I'm not sure if I should be one reading the
Yeah, Konrad,
section.
There have been some that have been answered that you might want to take a look at, and then there are some other new questions coming in.
I see. All right, so which one have been answered? Would this be the density matrix associated with the state psi? So Giulio asked if X is the density matrix associated to the state psi, and not necessarily. X is just one of the operators you are measuring. I try to avoid using the language of density matrices because it would take like 3 more slides and I would lose people like much more quickly. I just wanted to stick to the state vectors, and that's why I'm using all these convex sets. But no, I mean these x's are just the operators you are measuring essentially. All right, so let me see new questions. Are the dots in this plot expectation values or results of particular measurements of x1, x2? So I believe you are asking about plots like this. So these are the expectation values for a certain vector, because in each measurement you only get a single click, essentially, a single click of your experimental device, and you need to run your experiment with the same state a whole load of times to get the expectation value, and a single point is a result of a multiple runs of an experiment to get both of the expectation values. Can you explain the Gribner basis a little bit, please? Oh, that's that's a very complicated topic. That's a very complicated topic. I'm afraid, but in the most basic form, you could think about the Gribner basis as being tools to remove some of the variables from polynomial equations, and that's essentially what we have here. So we started with some polynomials, so that will be this determinant of this like matrix, with 3 variables, n1, n2, and lambda, and we just want to get a polynomial which encapsulates the properties of this set of polynomial equations, encapsulates the properties, but it has the n1 and the n2 completely removed. And that's like what you could think about Gribner basis, like being functional. So why numerical range technique is special in contrast to numerical analytical approaches, error, convenience, etc. Well, I just found it interesting from a mathematical point of view that you have all of these weird properties like the duality to spectrahedra and the possibility to sometimes have the analytical strict solutions to certain problems, and that's you are, if you view it as a linear maps from the sets of density matrices, or what has been done before, what has been asked before, linear maps from the set of density operators to this 3-dimensional space. You could view it as a structure which allows you to visualize the geometry of the set of quantum states, which is very high dimensional, but you just project it down. Project it down, remove all the unnecessary coordinates so that you arrive in just a 3-dimensional set like this, or 2-dimensional one, which encapsulates all the properties you are looking for in a certain problem. So for instance, the sum of variances. I believe there is essentially no other method which allows you to just get a solution, which is a root of certain polynomial, or almost an analytical solution as far as I'm considered. Okay, Julio asked a second question. From my basic understanding, in quantum computing, you want unitary operators. These unitaries with on X, would the numerical range change after applying the unitary? Is it easy to visualize? So if you would act, so numerical range is a completely static set, because you are calculating it for every state vector of, if you already know about the density operators, you are calculating for every state possible. And if you just apply a unitary to the set of states, to the entire set of states, you'll just get the same set of states. Therefore, the numerical range wouldn't change at all. And well, that's essentially the one of the parts of why this method even works, that you are trying to compress the entire information about all of the possible correlations for a quantum system into just a 3-dimensional set. All right. Are there any other questions? Not sure.
Well, perhaps this is a good point to wrap things up. Again, thank you so much, Konrad, for joining us. from Vienna today, and
Yes.
we're here in Champaign, Illinois, in the U.S. And it's great to have this this wide audience joining us. So look for upcoming announcements about additional opportunities for guest speaker webinars and other resources from Wolfram. Thanks everyone for being here, and we'll be in touch soon.
All right.
All right.
Yeah.
Bye-bye for
Thank
now.
you. Thank you very much.
Thank you, Konrad.